This is the first of 4 discussions for Chapter 19, which is the first chapter in our unit on sound. And we're going to start out with vibrations and waves. What we'll talk about in this brief video is a pendulum and give you a whole lot of definitions around describing a wave. We spent a lot of time at the beginning of the school year talking about motion. We talked about motion due to inertia, which has, if it has no force on it, an object will just keep moving at the same speed and direction that it has been. We also introduced adding a force to that, which would change the position or the velocity. So our big examples was rolling a bowling ball down the hallway, or throwing the bowling ball out, or dropping the bowling ball out the window. And we also looked at projectiles that had motion in 2 directions, like shooting a cannonball. That's all actually pretty simple motion. And when we talk about waves, we're going to do 2 things. We're going to talk about the source of it being a vibration, which it results in no displacement, but it's a source staying in place and basically wiggling, expending some kinetic energy, but not resulting in a substantial change in position. And when that wiggle is periodic and is transferred, then we're going to call that a wave. A wave goes from one place to another. Some sources of vibration need a medium to transmit through, like sound. Others, like an electromagnetic, does not. Another thing to think about waves is a wave that goes through a medium is affected by gravity and friction. So gravity can be the restoring force for some waves. For exceptionally tiny waves on the order of nanometers, you can actually have a surface tension effect as well. But vibrations which cause waves all come back to energy. And remember from our Newton's laws that energy is conserved. So when we talk about waves, we're going to show energy being transmitted from one place to another, but not necessarily matter being transmitted. So keep in mind that we start out with a vibration. That's a wiggle in time. Sometimes they are consistent, sometimes they are sporadic. And as we consider how that wiggle expands into time and space, then it will be a wave. Okay, your book will talk about the example of a pendulum. Let's review a pendulum real quick. We didn't spend a whole lot of time with this when we looked at angular momentum, but when we're talking about a pendulum, we've got a length that it's hanging from, we have a mass, and then we have a displacement in a certain position. So the weight is pulling it downwards, putting a tension in the spring, and then we displace it to the left and the right. All right? A force can be introduced to it, and then there'll be a restoring force that sends it back. You've got the forces are not balanced, which is what causes motion for us. All right? So picture the pendulum going back and forth, and eventually everybody loses the battle with gravity, or with friction, and it will stop in the equilibrium position. This is similar to the kind of motion that we've got. We've looked at the motion such as dropping our bowling ball off the roof, which is acceleration due to gravity, and then we use the Galileo experiment to slow that down by motions down the ramp. If you remember, both of these, did the mass of the object make a difference? When we threw the golf ball and the bowling ball out the window at the same time, they both landed at the same time. Likewise with going down a ramp. The same is true for the pendulum, that the mass at the end of the string doesn't change the motion of the pendulum. A couple of vocab words for you. This unit has got a lot of vocabulary. The amount of time that it takes the pendulum to go from one end to the other is the period. The longer the length of the pendulum, the longer the period. And this is exactly analogous to whether or not we drop the bowling ball out of a first-story window or a second-story window. It's the same kind of physics going on. All right, think about this for a minute and see if you can come up with an answer in your head. Supposing that you've got a 1 meter long pendulum with a mass of 1 kilogram, okay? And then you replace that with something double the mass. Does the period of the pendulum change? How does the period of the pendulum change? Does it double like the mass doubles? Does it halve like its inverse? Does it stay the same, or do we not know? Hey, just like tossing your bowling ball and the golf ball out the window, the mass doesn't matter. They stay the same. Good thing to remember is that the period of the pendulum depends only on the length of it. Changing the mass makes no difference. How about this one? Suppose that we've got a 1 meter long pendulum with a mass of 1 kilogram on the bottom, and we change that to a 2 meter long pendulum with the same mass. What happens to the period now? Is it going to increase or decrease? Is it going to stay the same, or do we not know? Hey, something to think about is this one, the short pendulum is kind of sort of like a cuckoo clock, and the long pendulum is kind of like a grandfather clock. And which one has a faster period when those clocks are running? And the solution to this one is that the pendulum will increase as the length of the pendulum increases. So period has the only thing that changes the period on the pendulum is the length of it. Let's give you a little bit more vocabulary. If I have that pendulum, and one of your videos shows a pendulum dripping sand, if you've got a hole in the bottom of your pendulum and we've got sand draining out of it and a conveyor running underneath it, we can see that when we track that pendulum going back and forth, it makes a sinusoidal wave. If you've not come across it before, when you see a wave like that, we call that a sine wave or a sinusoidal wave. And that's something that we observe. That is the shape of the motion going forward. Let me show you something else kind of cool. Remember when we did Hooke's law and showed that we can measure the springiness of a spring by its displacement with a certain mass. So this should look familiar. This is exactly like the experiment we did in class. However, when we did it in class, we let it be stationary, and we looked at the force going downward because of the mass and gravity, and the tension went in the spring upwards, and it was elastic, so it stretched. And we calculated that consistency. It's a consistent proportion for a given string. All right? What if we did something crazy with it, and instead of just hanging our mass, we gave it a tug? The scientific term for that might be that it would boing. And picture that spring or a rubber band, that it would go up and down. So we would pull it down, and then there would be a restoring force pulling it back up due to the elasticity of the spring. And it would go back and forth. It would go up and down until it too would lose the fight against friction. If we were to take a slow motion picture of that mass going up and down, it too would have a sinusoidal wave. This is a drawing of what we were just talking about. So the spring going up and down would give us a shape of a sine. Here is more vocab for you. There's just a lot in this chapter. You need to be able to remember amplitude and wavelength. Wavelength is the distance between the two peaks, which you'll see later are called crests. Or you can measure wavelength between the two troughs or any place in between. Amplitude is the distance, is the magnitude of the wave away from its midline. And it doesn't matter if when you've got a wave going through medium, like ripples in water or sound through air, or an electromagnetic wave, like a radio wave or light, these definitions apply to all the different kinds of waves. We also have crests and troughs. A little bit more discussion about how these apply to each other. The amplitude is the distance from the midpoint to the crest or the trough, and the wavelength would be one crest to another. Here's another important vocab word, the frequency, how frequently the source vibration occurs. The unit for frequency is the hertz. You've probably been familiar with that from sound. 1 hertz is 1 vibration per second. Something like a pendulum is going to be very low, very few vibrations per second. Sound is on the order of 100 or to 1,000 hertz. Radio waves are much higher, and cell phones are even higher than that. But they're all measured in hertz. And remember that hertz is vibrations per second. Frequency is another vocab word you're going to need to know, and it's how many vibrations are occurring in the second, and this is what we measure in hertz. Frequency is related to period. So the period of a wave is the time it takes to do one vibration, and the frequency is inversely related to the periods. So if the pendulum does 2 vibrations in 1 second, the frequency is 2 hertz, and the period of vibration is half a second. We will practice with these calculations. All right, supposing that we've got a sound wave with a frequency of 500 hertz. Remember, a hertz is 1 vibration per second. So what is the period of vibration? Well, period is the reciprocal of the frequency. So our period would be 1 divided by 500, or it would be 0.02 seconds. Remember that you can substitute instead of hertz, you can call that vibrations per second. Let's look at another one. So we've got a wave that has a frequency of 20 hertz, and if we want to understand what the period would be, the period is equal to the inverse of the frequency. And so that would be 1 divided by 20. Would be 1/20th of a second for its period. A couple more things to remember about waves. Waves transport energy and not matter. Energy and not matter. Think back to the Newton's cradles when the balls would hit each other and transmit energy from one to another, but not move themselves. Our wave speed is how fast that energy gets from one point to another. The good news is, in our class, we will not talk about wave velocity. We won't take into consideration any directions. We're only looking at the speed. And so an example would be if we have a wavelength of 1 meter and a frequency of 1 hertz. That means that the crest will arrive at a fixed point every second, 1 meter per second. Here's the last problem for this section. Suppose that we've got a wavelength of 10 meters with the crest, the crests are 10 meters apart, and they move past a fixed point every half a second. Our wave speed would be one of these choices. Wave speed is most easily calculated as the frequency times the wavelength. And the frequency is 1 divided by the period. Okay? Hey, after this section, when you see in class, be able to discuss these questions. What is a wiggle in time? And what if you have a wiggle in both space and time? What is the source of all waves? What does it mean to have the period in a pendulum? And what changes on a pendulum when we change the length of it? Also be able to talk about how a sine curve relates to a wave, and be working on the definitions for period, amplitude, wavelength, frequency. Be able to tell me what something like 101.7 megahertz means, and how do frequency and period relate. That's it. Thanks.